Thank you for the invitation. You're going to see some slides in a second, I think. But while we wait, I'll just say a few things about what I'm going to talk about. So my talk is on different kinds of adaptive interventions and experimental designs to optimize them. So one of the things I want to emphasize, I've really three things I want to emphasize in this talk. Number one, when we all talk about mobile health, I think everyone's brain goes to just-in-time adaptive interventions. But I also want to remind us that there are other, the way at least I think of building interventions is you have questions about interventions and then you have experimental designs to inform those questions. And I'm going to walk you through why mobile health can also benefit from ideas like sequential multiple assignment randomized trials or SMARTs, and then where MRTs fit in. And when I talk about MRTs, MRT is a micro-randomized trial. I'm going to just keep talking and pretending like this exists. So MRT is a micro-randomized trial. My second goal is to explain what an MRT is, but really delve into so I heard a lot of different discussions about the use of reinforcement learning algorithms and use of machine learning algorithms in real time to personalize messages. And I want to walk you through what that looks like and both the positives and the pain points of that to make you appreciate, if you're going to go into that world, what you have to do to be able to do that. And then the last point I want to make is on combining those two ideas of SMARTs and MRTs and work that I did with Billy Nahum Shani. I keep looking back because I can't, anyways. On hybrid designs, which combine ideas from SMARTs and MRTs to build sort of multimodal adaptive interventions, or MADIs, that's what we call them. I'm going to keep talking. I have a bunch of slides with pictures, which you're not going to see until they're up there. So what I'm going to walk you through, one of the things when I start talking to people about mobile health, and I start talking to people about, they say, I have a digital tool that I've developed, and I really want to build a micro-randomized trial. That's usually the sentence I hear. And I asked them why, and so we started talking about their study and what they're really interested in, and they start talking about the kind of questions they have about that tool. And often it turns out that what they don't want to do is an MRT. What they want to do is some other type of experimental design, because they're actually interested in other types of questions. And so the slide that you cannot see right now is a slide that we talk about different components of an intervention. So the way I think about them is human-delivered, digital, or human-delivered and digital. And I talk about intervention frameworks. So we have adaptive interventions, just-in-time adaptive interventions, and multimodal adaptive interventions, which you now can't see, but I want you to visualize a nice grid where you see three rows and 4 columns. Okay? Perfect. We're all having this mental image, exactly. So human-delivered, digital, human-delivered and digital. Intervention framework with AIs, JEDIs, and multimodal adaptive interventions. And then for each type of adaptive intervention, you have a different experimental design that you would employ to answer questions about those different types of interventions. So for adaptive interventions, we have, at this point now, it's been a long time, but we have SMARTs, sequential multiple assignment randomized trials. Everyone, so far so good. That's your top right corner of this fake table that we're all seeing together. We have the experimental design, which is the SMART. For JEDIs, or just-in-time adaptive interventions, you have the MRT. Okay, so this is the micro-randomized trial. These are trying to answer fundamentally different questions, and so we have a different design for those types of questions. And then it's not I guess the only negative of the last one is the term. So we call them hybrid experimental designs, or HEDs. They're not it's not as good of an acronym as SMART or MRT, but I came up with it, and statisticians are bad at naming things, so that's fine. And so there, if you have questions about both human-delivered and digital tools, you want to deploy both experimental designs to answer about each one separately. Okay? Since I have no slides, what I'm going to do is I'm going to walk you through an adaptive intervention blinded and point at some diagrams that you will not be able to see. Okay? So adaptive interventions, what are they? They're an intervention delivery framework that uses ongoing information about the person to decide whether and how to intervene. So the kind of AI I want you to think about is an adaptive intervention where you have individuals who are at the ED, and you can start them with a single session intervention plus a digital intervention, so they get a mobile app plus some single session intervention. And then after a month, you check in with them and you assess their response status. So you assess whether or not an individual is responding to the interventions you've already provided them. At that point, for non-responders, you additionally add remote health coaching. And for responders, you just continue with the intervention as is. So what I want you to visualize, since we have no slide, is a spot on the left-hand side with a big picture that says 1 session plus digital intervention, an arrow that points a month out, and at that point, you have an individual who will check on you to assess response status, and a nice bifurcation into 2 different parts with a responder and a non-responder. And for responders, it just says continue, and for non-responders, it says add digital or remote health coaching. Okay? So that's an AI. That is just a decision rule that tells you how to adapt based on incoming information about the individual. The incoming information is their response status at month 1. Okay? The adaptation is slow. When I say slow, it's you can think at the month or monthly scale. You're not monitoring their response status in that example at every single moment of every single day. You're just checking in at the end of the first month to see how they're doing. So when you think of an adaptive intervention, I'm trying to see if there's a tech person. Every time I see someone walk across the room, I assume it's the tech person about to save the day, but it's not this time. Okay. So the adaptive intervention is acting at a slow time scale, at the month time scale. And why I want you to think about this is because of adaptive interventions, you can answer questions at that time scale. So what you're interested in, for example, for an AI, is you might have some questions about this adaptive intervention, such as, at baseline, is it beneficial to start with remote health coaching or not? So when they leave the ED, you might have a question about whether or not I should include a remote health coach. Also, in my AI, I had non-responders getting remote health coaching. So another question you might ask is, at that month 1, what is the best thing to do for non-responders? Should I actually give you a remote health coach and step up, or should I just let you continue with what you have? At first, you have a question mark at the first stage and a question mark at the second stage. You don't know what to do for an individual when they leave the ED, and you don't know what to do when you assess response status and you're trying to figure out what to do with non-responders. So once you start having those types of questions, you should think about a sequential multiple assignment randomized trial. Just because we're doing this, and this is funny, originally the sequential multiple assignment randomized trial was called a SMAR, because Susan Murphy named it a sequential multiple assignment randomized trial, and so she thought it should be called a SMAR trial. Linda Collins convinced her that was a very bad name for something, and so that's why it's called a SMART. So that's a fun fact while we wait for this to pull up. So the SMART trial is a randomized trial where at each stage, each decision point, you have a randomization to answer a specific scientific question of interest. So at baseline, you have a question about what to do for an individual that leaves the ED. So you're going to randomize at that stage between options for that individual. At month 1, you're going to have non-responders, and you have questions about what to do for non-responders. And there again, once you have a question, the first thing you should think about is randomization, and here you're going to randomize non-responders to different options. The typical picture for a SMART that I can see that you cannot see is that bifurcation picture I was showing before is going to have additional arrows. So at this ED visit on the left, you're going to have a big R that's sitting there to mean randomized between different options. So you're going to have a big split right there. I'm going to just have to act it out like I'm a cheerleader for my own slides. You can't see. So you're going to have randomization there. At the second stage, when you see the non-response status, you also have a question there. And so you're going to randomize between step up and continue. And so you have a SMART will just look like the picture that you can't see that I'll show you once you can see them, in which you have response status that you have randomization at baseline and randomization at 1 month. Okay? So here is an example with 2 stages of randomization. In a SMART in general, you can have multiple stages of randomization. Maybe every single month you check in on an individual, you don't know what to do, and so you might randomize monthly to different intervention options. So the other type of intervention framework are just-in-time adaptive interventions. So I just want you to notice that with the human delivered, there is a digital component coming into play in that SMART that I showed you. There is a digital component in the digital intervention. That's just an app that you might deliver. So you might give someone an app or not. The remote health coach is also telehealth, so it's also using the phone to reach out to the coach itself. Here, what I'm talking about when I say digital is I'm going to be building a just-in-time adaptive intervention, which is going to adapt at faster time scales. And so it's going to need a different type of experimental design called the micro-randomized trial. So I want you to think about the following example. Now I can still point, but at least I don't have to make you visualize. So here's an example of a JEDI where I'm going to use ongoing information about risk to decide what to do on an individual. Here, I'm going to have every single day, I'm going to assess your level of risk, or the patient's risk, for a particular disease. So in this case, I want you to think of, I can give you a couple different examples. This is meant to be very generic. One example could be in the area of suicide research. I might look at something like suicidal intent, urge, and things of that nature to assess risk, and then based on that risk level, decide to send a message or not. You might also look at risk for substance use. You could think of risk in different domains. Here, if you're at high risk, I'm going to send a message, and if you're at low risk, I'm not going to send a message. So that's the example here. This is a JEDI, which takes in ongoing information. How you build risk could be many different ways. It could be just an EMA questionnaire, so I could just ask you about suicidal intent and urge. It could also be a risk prediction algorithm built using deep learning, et cetera. I'm being very agnostic to how you build this risk model. You can think of it incorporating sensors and such. But the decision is a very simple deterministic decision in the JEDI. If you're at high risk, send you a message, and if you're at low risk, don't send a message. But we're also going to, these is my little question marks that you didn't get to see before, so they're little birds with question marks, so that's fun. Here we're going to have also questions about building a JEDI. So when someone comes in and asks me about, I have a digital intervention I'm building and I have questions, sometimes what they mean is they have questions about when to deliver these types of messages. Is it better to deliver them when they're at high risk? Is it better to deliver them when they're at low risk? Is it better to deliver them on the weekends or the weekdays? Is it better to take into account things like, I think that was mentioned in prior talks, how busy the individual is? So I look at their Google Calendar, I notice that they're in a meeting, should I leave them alone? Things like that. So when we have these types of questions, we have an experimental design to answer those types of questions. So I just want you to notice it's the very same. So for AIs, we have smarts to answer questions about AIs. For JEDIs, we'll have MRTs. For an MRT is, again, sequential randomization. There's a couple key differences in an MRT that I want to point out. And then my goal today is to point out both the simple ones and then also point out some of the more difficult ones. So you are going to see sequential randomization in an MRT, but you're going to see it hundreds or thousands of times. So in a standard MRT, you may have randomization 4 times a day. An individual may be in the MRT for a couple months, so you're going to have hundreds of randomizations in such an MRT. Another example would be you might randomize potentially every minute to an intervention depending on the level of risk. So an example there would be I'm monitoring someone's location throughout the day, and so based on their location I might do something. In that case I have randomization every minute, and so you're going to have thousands of randomization times. And here again, you're using the R. So whenever you see an R, there's a scientific question behind that R. Kind of think of it that way. Here, we're randomizing individuals in an MRT every single day to message versus no message. So in this example, we have an EMA, and after the EMA, we randomize an individual at the end of the EMA to message no message. And we can answer different questions using MRT data. So for example, we can answer the question, is it beneficial to deliver a message in terms of reducing next day substance use, or under what conditions would delivering a message be beneficial? Now, when you see this, I want to point out a few things, and I'm going to go, yeah, I have plenty of time. I'm going to go over one example of an MRT that uses more advanced RL algorithms, but I want to point out a few things when you see this R and its relation to the SMART. So in a typical SMART, when you see an R in those SMART pictures, they typically mean 50-50 randomization. You're just doing simple coin flips. In an MRT, you are usually not doing that, and there's a couple reasons why. So number one, let's just think of a simple randomization scheme where I'm just always flipping a coin that has some probability associated with it. Here, if I used 50-50 over the course of a week, So over roughly 6 days, you'd average write 3 messages on average for that person over 6 days, or 3.5 over 7. And that means that you're having a dose associated with the randomization scheme. So whenever you choose an R, a randomization probability in an MRT, you're actually picking a dose, an average dose for the individual. So a lot of the times in simple MRTs, what you'll see when they choose the probability of treatment, it's associated with what dose can we typically expect someone to tolerate in this population. So in the case of a physical activity study where we have roughly 4 messages a day, or 4 rather decision points a day, we might decide that on average 1 message a day is tolerable in that population, which means you choose 1 over 4 as your randomization probability. So that's a very different mentality than a SMART, where in a SMART you're just doing 50-50 because you're trying to get balance to have the most power to detect effects. Here, what randomization you choose is actually informing a policy for how you treat people. So if I choose, if I choose probability 50-50 in my example of 4 decision points a day, I would on average send you 2 messages a day. That may be good, that may be bad. Usually what we tell people is to talk to domain experts, talk to people in that population to understand what they could tolerate. So in a suicide population where we're studying after the ED, it may be the case that they'd only tolerate 1 or 2 interventions a day. In other populations, they may tolerate more or tolerate less. Regardless, we have now randomization at a fast time scale. So here you can think of randomization daily or multiple times a day. And they're still going to answer questions about how to sequence and adapt at this faster time scale. So one example here is, again, going back to my question of, is it beneficial to deliver a message in terms of reducing next-day substance use? What we can do is we can look at all of these different times at which we sent the intervention. We can measure substance use on the next day, and we can look at whether or not the sending message was more likely to reduce next-day substance use than not. Now, I think Pedja mentioned this and others. This is a time-varying effect, because these messages, often you'll see an effect early on in the study, but later on in the study that effect will dissipate. I'll show you a few pictures down the road. And so often we don't just care about whether or not there's an effect, but under what conditions would delivering this message be beneficial. So in the example of my Jedi, I had high and low risk, and so this MRT gives me data to assess whether or not interventions are more effective at high risk versus low risk. So the way I would do that is I would stratify all these times, and I would look at high-risk times and look at the treatment effect at those times and see if it's larger than at the low-risk times. This is all well and good, and I'm not going to try it. So my goal was not to scare you with my next set of slides for the next 10 minutes, but I want to talk about, often people do an MRT to then move towards personalization and using reinforcement learning algorithms. I'm going to talk about that in a second. I want to disentangle 2 different things, though. One is personalization of the intervention content, and one is personalization of this R, or this randomization scheme. So when I send you a message here, in my simple case where I send, let's say, with probability 3/5 in this picture, so with probability 3/5 every day I send a message, so that I get, out of 5 days, I get on average 3 messages in those 5 days. The message content can be tailored to you as a person. So it can use information about you and use your data that's been collected to be part of that message. So that's a tailored message, okay? But the randomization, so when I say personalization and we talk about reinforcement learning, what we're trying to personalize in that case is the R, how and when we're sending these messages. In this simple MRT, if I always send with probability 3/5, I'm not taking into account your context when sending a message versus not. And so often what people want to do is not just personalize the messages, but personalize when we send you the messages. And so we've done some work, Mike, who was talking earlier, Juan, Ethan, Rachel, and Madeline have all helped with designing an MRT that tries to personalize this randomization scheme to an individual. What I'd like to walk you through for about 10, 15 minutes is the difficulties in doing that. So again, I'm not trying to scare anyone here, but I think what I often hear people do is they get excited about AI and RL and things, and they just go, we're going to run a reinforcement learning algorithm in my app, and it's going to be awesome, which is great. But what I want to talk about is all the decisions that go into building in these types of algorithms into that personalization. So Mike's work is in the area of hypertensive populations and reducing sodium intake. This is the Low Salt for Life app. And here we're building a contextual mobile app-based intervention. The design for Low Salt for Life was a randomization at baseline to a no app and a low salt app for 6 months, where the primary outcome was change in urinary sodium excretion. What I'm going to focus on is a micro-randomized trial embedded in the Low Salt for Life app that tries to target engagement with the Low Salt for Life content. Okay? The way that the MRT was designed was we had to first decide when are we going to potentially even send you a message. Okay? So going back to my picture, my first picture where you just saw the R's at the daily basis, that would be a case in which you just randomize maybe every morning to whether or not you see a message. Here what we're going to do is we're going to ask, well, what context would it even be worth sending you a message? Okay? And what we decided is that we would only send messages when someone was at a grocery store or restaurant. Now, how do you do that? Well, there's like many moving parts. Let me just say a few things. I'm not a software engineer, so I'm not going to talk about how exactly you do it, but you need to first follow the individual, know their GPS location. Not only that, you need to know where every grocery store or restaurant is that they might be going to. That is a non-trivial task that I'm spending that amount of text on. So we're pretending that that system is built and is pretty reliable, okay? What we're going to do is when you get to those locations, we're going to flip a coin. In a simple MRT, this would just be a probability, a simple probability, but we're going to improve and personalize that probability. And with some probability, we're going to send you a message that tries to get you to use the app in the next 30 minutes. The app contains a bunch of information about improving your low sodium options and giving you low sodium alternatives when you're at the grocery store or restaurant. So my goal is not the same as the full lows. My goal inside of my personalization is not to try and improve the distal outcome of sodium excretion, but it's just to try and improve your engagement with the app in the proximal time, okay? So my goal is to use passively collected contextual information to optimize the delivery of these notifications. So it may be the case, I'm not telling you this is true, but it may be the case that at grocery stores, I go to the grocery store with my son, it's not the best time to send me a message because I'm usually just chasing him through the grocery store. But at a restaurant, maybe he might listen and sit down for a little bit, and so I might be able to, when looking at the menu, use the Low Salt for Life app. And that's something we're trying to pick up on, is how to figure out which of these two times is more useful to send messages. Another example would be week versus weekend. It may be that on the weekends I'm just busy and I'm just running to the grocery store, but on the weekdays I'm doing it at a specific time, and so I might be more willing to engage with the app. The other goal is to prevent user fatigue. So we don't want to send notifications when all that's going to happen is you're not going to use the app and we're adding to your burden that already exists. So we want to have these notifications only at times when we think that they're most useful. So the way we did this, and the optimization scheme, was to update this algorithm. And the algorithm, for those of you, so I, as a statistician, have to have 2 or 3 equations in any talk I give. You're getting 2 equations. I said no more, but that is the number. I had to give at least 2. So what we're going to do here is we're going to use Bayesian logistic regression. So for those of you, most of you have at least heard of logistic regression. It's just the fact that my outcome of interest is engagement, which is a binary variable. So in that case, your very typical regression modeling approach would be to use a logistic regression. The second question is why Bayesian? So Bayesian is, I'm going to show you all the benefits of it in a second, but the way I want you to think about it is whenever you start trying to figure out how to personalize, there's a trade-off. I have to figure out the best times to exploit. If I know that a certain context is good to send you messages, I want to exploit that fact and send you messages in those contexts. But I also want to learn. So I have to explore all the possibilities of when I could send you messages. And so in any of these algorithms that we design for RL, there's basically an explore-exploit trade-off. I need to make sure I'm sending you messages often enough in different contexts to figure out what works, and then also increase the probabilities in those contexts so that I'm exploiting the ones that work better. So the Bayesian machinery gives you a nice way to balance those two things. The number of times you go to the grocery store is limited. I go to the grocery store maybe 3 to 4 times a week. That's mostly because my kid likes Hot Wheels and we go get Hot Wheels. So that's, you got to get Hot Wheels somewhere, and Kroger has a good selection. The average person is only going to go a few times a week, which means that the number of data points any week on an individual is quite low. I'm not going to see you using the app frequently, which means if I update every week, I'm not going to have much data about you. So we decided to update every 2 months this algorithm. The algorithm is going to optimize the personalization at the 2-month scale. So we have enough information about you to know how to improve our algorithm. So just to give you a picture of how this MRT worked is we have month 0 enrollment. For the first stage, we just do a pure exploration policy where we send with probability 0.8. So this is the MRT I showed you, the really simple one with the R that points in the constant probabilities. And then at month 2, we try and optimize and give you context-specific notification probabilities. And we re-optimize at month 4. There's like a million practical challenges. I want to highlight 4. One is defining a relevant proximal outcome. I'm going to talk about that in a sec. The second is building this model. So I said I'm using logistic regression, but there's many choices you have to make when you say I'm going to build a model. I want to show you how we think about building this model. The third is balancing model flexibility with computational cost. So if we build a really complicated model, it is often more brittle. If it's brittle, it's going to break, and I'm running a trial that I can't have things break in. So we have this tension between building a flexible model and building a model that works. And the last one is dealing with missing data. So a lot of people will use mobile health data retrospectively, and they'll look at a data set and say, oh, like I can just analyze it and there's not a big deal. What do you mean missing data? Why is it a big deal? Because anytime I arrive at a grocery store, I can't rely on my entire context vector to always be available. So what I mean is, the app needs to know, my context might include things like whether you're not at a grocery store or restaurant, but also what the weather is, let's just say. But sometimes the weather API goes down, or sometimes you write code and it just breaks, and so you can't access the weather API. If you want an algorithm if you want to design one of these RL agents, you need to have a way to handle all of these sort of edge cases. And I'm just going to talk a little about how we did that in this context. So my goal, describing important factors and some pragmatic solutions. So for the relevant proximal outcome, we wanted one that was easy and reliable and sort of targeted engagement. So what we just looked at is whether or not you use the app in the next 30 minutes. So it's a binary indicator of whether or not you open the app at all. Did you go to any landing page? Did you look at anything? Did you input any information? Any engagement with the app, we counted as a 1. Okay? There is a lot of work in the RL language, it's called reward shaping, which is fancy talk for I had to put some thought in how to build my outcome. What I just want to say is that with data collected in these types of trials, you can do a better job. So this is just a first pass on how to do that. I said I'm a statistician, I had to have a few equations. So here's my I warned you I was going to show you a logistic regression, so here it is. When we want to build a robust statistical model, and you have data, but the context, you're getting context slowly over time, you have very little data early on. So the first person in my study, the first time I do my update, I'm gonna have like 20 observations, right? But the 100th person in my study, I'm gonna have lots of data on all the people that come up before. And so the way we handle that is we just build a model that slowly grows over time and also penalizes a lot of terms so that they're really small, so it doesn't break the system. So what we call these are shrinkage priors. It basically improves stability, so our algorithm never breaks. And we use a hierarchical model to partially pool information across people. So what we try and do is we basically say everyone in our study is somewhat similar to one another. And so we're going to try and use information on past participants in the study to help me personalize faster on the next person. Okay? The model flexibility with computational cost. So here what we have to do is we have to build a model. So what I think Pedja was talking about, Mark Newman's building this P-JEDI's Justin framework. I think that's what he talked about. That's great in many ways. It's really good for building sort of prototypical P-JEDI's in the future. It's, as he said, I think Mark's about a third of the way done. Right now, what you have to do if you want to build an RL agent is you also not only have to fit a logistic regression, but you have to tell me what specific model are you proposing? What variables are you going to use? Are you going to include interactions among those variables? Are you going to standardize those variables, etc.? There's a lot of decisions that go into building the model. What I'm just going to highlight here is, as you get more data, you may want your model to be more flexible. So when you have 10 data points, you're not going to fit a model with 20 variables in it. That's, almost like Stat 101 level. Just like if you have 5 observations, you're never going to learn a model with 20 variables or 30 variables. But if you have thousands of observations, you might be able to parse out and include more interactions. And so what Madeline built was a nice sort of pipeline for building more complicated models as we got more data. And then the last one, again, as I mentioned, is missing data. So here, the 3 types of missingness we could have is, actually we have 2 types of missingness I want to highlight. One is just missing data. So I never get to see your temperature because the temperature API broke. That's the example I gave before. Another example is just, we started our study in June, and it's hot in June. And now it is March, and I've never seen someone in cold weather in my algorithm before. What do I do? It's a new context I've never seen before. The algorithm needs to figure out how to sort of pool information across those 2. And so that's actually missing in some sense. For the practitioners, what I want you to think of here is what we did is we took this data. This is the input. So the algorithm, the way it worked is, and this is where Ethan, Juan, it took us a long time, but Ethan and Juan are software engineers. Mike was the PI. Madeline and I were the statisticians. We all thought we were saying the same thing for a long time, and like half the battle was just realizing we were talking past each other. And this is kind of the schematic to like help us all understand what we were doing together. So what we did, we decided that the algorithm would just take as an input the following table. So this is all the contextual information, the notification type, where you were, what the weather was, what time of day, were you engaged in the past week, did we send it or not, and did you open the app? We would fit this gigantic logistic regression with all these hierarchical terms. It looks like this at the output. It's all fancy and nice. But what we would make, and then we would decide, should we, in different contexts, send you a message based on this model that we fit? What it basically boils down to is, if sending a message makes it more likely for you to engage, the model would say, hey, you should send it with high probability. That's how it works. What this doesn't account for is delayed negative effects of burden. And so there are ways to account for that, which we didn't do, just mostly because it's quite difficult. At the end of the day, what we build is every month, every second month for an individual in our study, we decide, I don't know how it came about. We call this the mega table. It is every possible configuration of your context, we would have the randomization probability from our algorithm in that thing. So every version of notification type, situation, weather, time type, and engagement, every configuration would have a randomization probability associated with it. And this whole table, I think, is like 15,000 columns or rows. The reason we did this, it is not the most efficient way to do things. It was because the handoff on an engineering side was much easier. We could build this huge table, upload it into the system, and then the software engineers only ever had to look up in the table that information, and so it was really easy to deploy in the study. If we tried to do something more in real time, we would actually have to build a lot more on the engineering side. So this was more of a compromise between the engineering team, who didn't want to have to build on-the-fly support for an RL agent, and the statistical team that could build this table for them. Okay, you said I can go. I'm going to go over by just a little bit. No, it's fine. I wanted to make 2 more points, and then I'll stop, which is, this is all great, and I think what a lot of people talked about today was the building of the RL agent. The problem is then you have to run the study, and someone has the painful task of monitoring the agent. So this isn't patient monitoring that we're used to. This is monitoring of an algorithm that you're using on people because you're worried about how it's performing and whether it's breaking and doing really bad things. So what are the bad things it could do? Well, one thing it could do is it could just go off the rails and just be like, I'm sending it all the time, or like, I'm never sending it, or I have no idea what to do, so it's broken and it's sitting on the cloud and it breaks the whole Low Salt for Life app, and Mike is yelling at me and it's a crisis, right? And we don't want that to happen. And so what ended up happening is we had Madeline and then Rachel basically every week have to do a monitoring of the app. So you can kind of think of it as like a study coordinator for the algorithm kind of thing. What it would look like is a report that we gave. So Rachel and Madeline wrote this for me, and then I would share it with the study team if we needed to, in which we would monitor locally whether or not what we're seeing in the cloud matches what we would expect locally. So this is the kind of plots that we would show people. So here is an example of an individual. I just randomly selected it where our local fit looks a lot like the cloud fit, so we didn't really see anything going wrong. The variables that it was seeing were significant, looks good. Here, just to show you an interesting fact, this person, on a holiday or a weekend, the algorithm's pretty confident it should be sending you messages, but on a weekday, it's saying lower the probability significantly for that individual. So this is just someone where there's some level of potential personalization going on. We also did a bunch of calibration tests. So this is just again, I will say Madeline and Rachel were I did not run any of this. They ran on a sort of regular basis these reports for every individual coming through the study every time we did an update. And so here, this is just a calibration plot to show that hey, what we're getting looks like what we should get. And the other plot on the right, it should not scare you, but this is just to show you that over time, what we were curious about was whether or not early in the study, the first update at month 2 looks a lot like the month 4 update. And here it's showing it's actually doing something different. So it's just showing you, okay, there's something going on in those figures. This last one is the kind of case you get when things are going off the rails. So this is just to show you our local is really confident it should be sending, but the cloud is not. And so what this does is it makes Rachel and Madeline have a panic attack. They send me the information, and we have a group meeting to figure out what's going on. So what ended up happening is there was a software update halfway through the study, and it broke one of the pipelines for the outcome data. And so what they were fitting on the cloud was not matching what we were getting. And so we had to go back and fix all of those things. So this is sort of a nice thing where, again, when you deploy these RL agents, you're not only saying, as a statistician, we're often thinking about being involved early on in the design. Then we kind of walk away for a little bit, and we come back at the end when the study's over, and we talk to everybody about how the study went and try and analyze the data. I'm not saying you should do that, but that's often what happens. Here, if you're going to deploy an RL agent, you're committing to this kind of monitoring over the course of the study. And with software systems, they break, right? Not only do they break, but they break your system pretty badly, and you have to go into a week-long panic to figure out what's going on, and then you have to figure out how to fix it, and then you have to figure out how you're going to report it as part of your protocol, and all those types of things. And so this is just our picture. And so what we had is Rachel and Madeline kept a log of all the times we thought we saw a break, what we found out that was, how we fixed it, and that way we can include it as part of the report. Of course, what you're probably more interested in is the actual, did we actually see any personalization? And here we're just showing some level of personalization. This was about a couple months ago. So for some individuals, it's actually very unlikely we should be sending messages regardless of context. For some individuals, it was good to send pretty often. This plot on the far right is just showing, it's hard to see. I just want to point out this person in the bottom left corner, just to show what we often will see is that restaurants, the probabilities are often higher than for grocery stores. So we do see some differentiation between those. But we do see a lot of movement towards the boundary on the 0.95 side. Okay, I'll make one more point and then I'll stop. I'll leave the last point as sort of a teaser. You can talk to me later if you want. Of course, once you have the data, what do you do with the data, right? So that was how we actually run an RL agent. Now we want to assess whether or not we see effects in the data after the study is over. And so what's different about an MRT is you have not just one outcome at the end of the study, but you're often interested in how does my treatment affect this proximal outcome over the course of the study. And so what we have is we have methods to analyze the effect over time. So what I'm showing you here is Jesse's Valentine study with Brahmaji. So that was the study team I showed you here. And Peja sort of alluded to this in his panel discussion, where you have both Apple and Fitbit users in the study. We realized because we had two wearables, we didn't want to combine them and pretend that Apple and Fitbit measures were the same, so we analyzed them separately. Here's the effect on step count over different phases in our study. So phase 1 is the first, I think, 2 months, and then phase 2 is the next little window of time, and phase 3 is later. What you see is a significant effect for Fitbit in that first phase, and then it dissipates over time. This is sort of your standard time-varying effect you'll see in an MRT, which is early on, you might see an effect, but later on you won't. I will end with one thing, which is we don't really care about the time-varying effect by itself. What we care about is what variables should I have included in my future RL agent, right? What things should I include to personalize? And what ends up happening there is you do a lot of exploratory analysis. What I would just say is that the exploratory analysis should be guided both by domain science, but also account for all of that exploration you're doing. And so what we have here is an interesting method. I'm not going to talk about it in detail, but the method basically accounts for that data, the double dipping in your exploration phase. So what you're doing is you'll throw a bunch of variables into this analysis. It'll try and select the ones it thinks is significant, and then it'll account for that selection as part of building these confidence intervals. So the normal thing you might hear is like, don't do selection and then you double dip so your confidence bands are off. This method tries to account for that. I just want to end with this, which is it's really interesting what we were finding here. Ramaji and Jesse aren't here, but I'm going to show this to them later. It turned out that time-varying effect I was talking about, so we saw an effect early on and late on we saw less of an effect. It's more because we were averaging over how much steps people were taking as part of the study. So what we saw, I'm going to highlight one particular thing to see these 2 lines here, is individuals who had a high baseline step count, there was a large significant effect. So you see this line here, baseline steps, you see it roughly at 4, that's saying, okay, if you're someone who's already active, sending you notification messages to try and get you active was effective. It's not that time and study mattered, what actually it ends up picking up is how much do you walk during the study. So if you're walking a ton, the effect dissipates faster. So it's not the time scale isn't time and study, it's actually how active are you being. And so what matters in terms of when we should send messages is how active have you been in the recent past. Are you currently someone who's walked a ton since the beginning of the study? Then this effect would dissipate. If you haven't walked that much, we should continue sending you messages. All right, I'm going to leave as a teaser this last one, which is the multimodal adaptive. Basically, it's just saying, if you have questions about both human delivered and digital, why don't you think about combining them? And so we have methods to do that. But because of time, I'm going to stop there and answer any questions you have. And this is I've never built this. This is fancy stuff from D3C of a QR code for where there's a bunch of software and different examples of MRTs and JEDIs and smarts and MRTs, just to kind of get a sense of how things work. Thank you. Oh, questions, yeah.
I'll ask one. I know the answer, but I want you to disseminate this to everybody. So for the people here that want to incorporate one of these, can I call them R trials? Is that okay?
Yeah, go ahead.
or incorporate reinforcement learning in general into one of their studies, and they need your group's help. How do they get started?
Yeah, so I think there's 2 different parts. So number one is just you can reach out to the D3C, and we have both a brain. So there's a couple different things the D3C does just generally, which is one is if you're just building a grant around adaptive interventions and you want feedback, we do have brainstorms we've been running where we have individuals who are writing grants come in and talk to us about what they're working on. All the information belongs to that individual. We do not say you have to work with us. It's all just about trying to help you understand what are your actual scientific questions, what designs do you actually need to answer those questions and things like that. For the RL side, we have Payow's in the audience somewhere. There he is, Payow. So we have a bunch of software engineers and stuff. I'm not signing you up, Payow. Do not worry. I know, yeah, no worries. But we do have a lot of individuals deploying and running these RL agents and building the frameworks. If you're interested in using them, we can talk about how you can use them. If you're interested in working with us more directly, like with the Mike study, I think talking to us individually would work. The biggest thing with the RL is Mike had a software engineering team he already had in-house to help facilitate everything. It would have been an impossible task for us to try and spin it up independently of him having software engineers who were going to help with deployment. We were only tasked with building the RL agent and helping translate that agent into a system they could use as part of the app. But we were not tasked with actually building the pipelines of connecting the app to our actual RL agent. And that was, it really can't, you need both a really good, strong software engineering team and a good statistical team to do that. Yeah. Dave.
Walter.
Yes.
I have a more philosophical question.
Okay.
So in this whole RL stuff, how tabula rasa is your first state space? What's the minimum amount of information you need to start? And how do you make determinations for when you optimize or, or demonstrate that some of these rules are, making a reliable difference in the prediction of a person's behavior?
So I think 2 to 3 things. So number one, I think just from a purely how I think about these designs in general is I do not think you're ever going to be in a situation in which you run a single MRT, you figure out all the variables that are important, and you just go on and build an RL and let it go and you're done. Susan was here for the eHail seminar of a while back and had this picture of sort of the continual nature of optimization in this world, right? So it's never a situation in which you just sort of finish or you run one study and you're done. The way I think about it is often you won't have much information about what context matters. You have a sense of what data to collect to maybe ask those questions. So you'll have a list of maybe 4 to 6 variables you think may be useful for moderating the treatment effect. But in a first MRT, you may not even use them as part of an RL agent. You might just have a dose constraint with that 0.6 or 0.7. After that, that list of 6 is going to become 2. You might add a few, you might find a couple that you didn't know that you might add, but the list is still going to be short. It's okay to have an RL agent that doesn't have a ton of variables as part of it, is my first point. It's still going to potentially personalize if those effects are somewhat significant. And so it's going to target proximal behavior. The point I was making about building this adaptive thing is even with 4 variables, if they have different levels or that you think the effect is nonlinear or you think there's interactions among them, then with 4 variables, you can still have a very complicated model. And so you still have to think a little bit about what the model looks like. To your point about, and so then you just sort of iterate between those 2 procedures where you run a study where you think you have the best set possible, you then look after the study to see which ones weren't that useful, which ones were useful, but you're still targeting, I think to your point, proximal behavior. You're looking at like, this agent's just trying to do a good job on this local thing. Do I actually improve the distal, right? And I think there's 2 different, not 2 different, there's a couple different ways you can go about it. One is to actually just have an arm where you don't do the personalization. And you just say, okay, I'm gonna look at distal under this. Once you have an RL agent you think could be improved, but at least is doing decently well, you might just have baseline randomization to you get a simple version and you get the personalized version and you look at a distal outcome. That's kind of like what Low Salt for Life does. The issue there, and it's not an issue, it's more like you have to have some confidence that the RL agent's gonna do well and gonna do well for the distal before you get to that stage because you're throwing away a lot of power in building an RL agent. Basically, you're taking half your sample and saying, don't look at this when you're building your RL agent. So I think it's definitely down the road. I think there's still a lot of question marks about whether proximal behavior leads to the distal outcomes and also mediational questions about whether or not those effects are actually through the pathways that you're trying to optimize over. But those are data questions I think that you ask after you kind of built the agent.
That's awesome. One follow-up question. Yeah. You said at one point that your RL for person 1 is different than your RL for person 100. Mm-hmm. Are there any general statements you would make about the degree to which you inform the behavior or the push for person 101 from person 101's past behavior versus a sample of 101 people?
Yeah. So I think, no, that's a great question. So there's a general notion, I'm going to talk in stats terms and try and translate it outside of there. So there's a general notion, right, of how much variation do you see across people versus how much variation do you see within a person. So let's just assume no one changes over time for a second, okay? Which is not true, but just for this mental exercise, think that. Then how much I should use other people as well. If there's a lot of variation across people, then you look nothing like anyone else, and so I should really not use much of that old data to inform what I do on you. If basically everyone looks the same, then you should pool as much as possible. That's sort of so we get very data adaptive in how much pooling we do because of that. My other point is just we change over time, right? So I think Pedja talked about you hurt yourself when you're working out, and so you go off, but then you come back. You're not necessarily the same person you were in terms of being an athlete. And so in that context, I think because people vary over time as well, that pooling also has to think not just about how much are you similar to you in the past, but how similar are you at your current moment to how other people were in those moments. And so you have to account for both the across person heterogeneity and across time heterogeneity within a person. And that's why the pooling matters a lot, is that what we found is even if there's a lot of heterogeneity across people and across time, pooling just gives you so much more information and allows you to shrink towards something useful. And so you just learn a lot faster. Even though it's a little bit biased, you learn much faster than if I just rely on one person. I think we're at time, so. Oh, you have, so, okay. I saw someone, I don't want to stop him from asking a question.
So a lot of the earlier talks were about mobile and wearable devices for measurement. Mm-hmm. And I was wondering if you could maybe give some thoughts on imperfect measures that maybe aren't gold standard, yep. But how would an RL use them and you still find them useful? Yeah.
So I think a couple of you were at the FAIR Summit which was 2-3 weeks. I don't even know how long. It was a couple weeks ago. Weeks? Months? Who knows? So we had a summit in which we had individuals. We had a discussion. I had a discussion with a quant psychologist there about measurement. And his goal when talking about measurement was to get a perfect gold standard measure of something of interest. So he wanted to make sure it's real step count. And from a perspective of intervention development, while I do care that it is somewhat that when I'm talking about the effect of the moderation effect of prior steps, what I should really be saying is the moderation effect of Fitbit measured steps. And what I care about is often from an intervention perspective is this thing that I'm measuring useful for making decisions? So it could be the case that Fitbit step count is not real step, it's correlated, but it's not real step count. But it could be that it's just a very useful measure for when making decisions. And so in that case, I don't care, I don't necessarily I don't have to think about it as a gold standard. This comes up a lot with deciding whether or not we see intervention effects in these MRTs, which is if I want to talk about the effect on a proximal outcome and I have missing data, do I impute the missing data or do I just treat it like missing? And what I mean is if I have missing step count data, if I impute it, what I'm really estimating is the effect of the steps if I had seen it, but I don't see it, right? Because in a real MRT, I'm not going to see it. And so I really just care, the missingness can be much more helpful for making decisions in those contexts. And so I think to give a shout out, there's Jamie. So Jamie and others in our group have worked a lot on missing data and thinking about missing data in the context of building these just-in-time adaptive interventions. So that's, I think, very different than your traditional statistical missing data problems. Okay. I don't see anyone in Creep else going up to the mic, so thank you, everybody.